Starting with the name of Allah, who's Rahman and Rahim. Today we will be presenting about our final year project, which title is Design of Permanent Free Motor for Electric Vehicle Application. I myself, Engineer Shah Faisal, and along with my group mate, Engineer Abdul Qadir, we are being supervised by Dr. Qasim Ali and co-supervised by Engineer Ghulam Akbar. Introduction, as we have been the world is recently increased attention towards electric vehicles, and due to which increased fuel cost, security of fuel, carbon dioxide, and other internal combustion engine emission concerns. In over a year, just one electric car on the roads can save an average 1.5 million grams of CO2. The commercially dominant electric vehicles traction motors that are being used are permanent magnet, synchronous motors, and induction motors. But recently has been interest in one field synchronous motor. Motivations that how we go towards our titles or to our projects to support the clean energy movement is to rapid growth in adoption of electric vehicles and to reduce cost of electric vehicle motors. Last, to replace permanent magnets used in motors. Problem statement: in permanent magnets does have constant field and we cannot vary that field. So varying speed of motor due to permanent magnet motor is very difficult. Rare earth permanent magnet materials are subject to market volatility, and the cost of permanent magnet motor is very high. Literature, we have been studied four paper in which the first title PM assisted pushless wands rotor synchronous machine, in which the permanent magnets motor are used being carried out in this paper, and the performance of permanent magnets synchronous motor is compared with that of. And in the second paper, comparison of traction motors that reduce or eliminate rare earth materials. In this paper, the comparison of non-PM motors and PM motors have been carried, and almost the same power density can be achieved with the non-PM motors as those of PM motors. And a trade-off is required between cost and power density. And the third paper, design of three-phase square cage induction motor for electric propulsion system. In this paper, 5 horsepower motor is being designed on NSYS for electric propulsion, and its efficiency and torque characteristics are analyzed. And the fourth paper, permanent magnet synchronous motor for electric vehicle applications. In this paper, an annular rotor permanent magnet synchronous motor rating 5 horsepower is being designed for electric vehicle applications, and the design, produce, analyze are achieved by using NSYS Maxwell. The aims and objectives of our project. Our first aim is to replace those permanent magnets used in motors. Design of wound field synchronous motors and induction motors, and comparison of wound field synchronous machine and induction motor initial models, and improving power density of wound field synchronous motor. Methodology that we have been carried throughout our project, that is literature review, design calculations, design on NSYS, comparing the initial models and choosing the best model, and improving the power and density of that model. In calculations, we have been carried these formulas for its design parameters or calculations. Our coefficients, power loss in gap, stator inner diameter, pole pitch, flux per pole, stator teeth weight, and these all are the equations that we have been used for wound field synchronous motors, and these are the equations that we have been carried for induction motors. Methodologies, the software that we have been using for the designing, that's NSYS Maxwell. NSYS Maxwell is an electric electromagnetic field servo for electric machines, transformer, wireless charging, etc. We can model and analyze electrical machine using this software in Maxwell. Results and discussions. We have been designed the two initial models, wound field synchronous motor and induction motor. Wound field synchronous, we have two parts, this stator and rotors, and same as for induction motor, stator and rotors. These are the two models that have been designed initially. And results and discussions. In result discussion, the wound field synchronous motor parameters and the induction motor parameters, that and they both are being rated as 1 kilowatt power, 1 kilowatt, and their operating speeds is same. Other are the parameters that we have been calculated from the above equations. Results and discussions. Result in discussion. Initially, we have been compared wound field synchronous motor and induction motor in terms of its start and efficiency. At different currents inputs, we have been analyzed, and this is the torque that we have been achieved at 2 ampere input current. That is, its average is 1.8722. And the wound field synchronous motor torque at input current I is at 8 ampere, that is 20.5 Newton meter. And that's the torque of induction motor at input current 2 ampere, that we have been achieved almost 1.32 average Newton meter. And the input torque at 8 ampere, that is 9.75 Newton meter. Now the comparison of wound field synchronous motor versus induction motor torque comparison. We have been compared its torque in different input currents. These are the input currents that we have been carried. That is, the blue curve shows the input current, the orange is for the induction motor torque, and the purple one is for the wound field synchronous motor torque. So we have been compared that we have analyzed that the wound field synchronous motor has higher torque density rather than the induction motor. So now the core losses for these two motors, wound field synchronous 8 ampere is its core loss is almost 102.5 watt its loss, and induction motor core loss is 150 watt, means it's is higher. Induction motor has higher losses rather than wound field synchronous motor. So wound field synchronous motor and induction motor efficiency comparison. So we have been compared its efficiency in terms of torque as well as efficiency comparison. And so from this we have concluded that wound field synchronous motor has higher torque density, capability and efficiency. So hence we have been carried wound field synchronous motor to increase its power density up to 60 kilowatt. So wound field synchronous motors power density improved model. This is the model of 60 kilowatt motor of wound field synchronous that we have been improved its density. These are the parameters, that is its rated torque is 207 and rated speed is 27 and 68. Now the torque and power speed characteristic curves. So as we know that the important characteristics of electric vehicle is its torque speed curves. So the electric vehicle is operating on different speeds in different regions. So this is the constant torque region and this is the constant power regions. So operation below rated speed. Now we have been analyzed it at different speeds. At rated speed, below rated speed, and above rated speeds. So it below rated speed, when we decrease the speed of the motor, its torque remains constant. while the power decreases. This region is called the constant torque region. And now to operate the motor below its rated speed, to keep its torque constant, we need to change its frequency accordingly. So that's the formula that we have been used for finding out the frequency. Stator induced voltages. So these are the voltages that we are induced in the stator windings. And the torque that we have been achieved is at this frequency is 208.86 Newton meter, and the core losses is 138.7 watt. Magnetic field density. Magnetic field density is the flux flowing through per unit areas. These are the different values that shows the magnetic field density. So the blue area shows that the magnetic flux passing through that area is almost zero, or that is not passing there. Operation of it above rated speeds. So when we increase the speed, its power remains constant while torque decreases. So this region is called a constant power regions. To operate motor above a rated speed while keeping power constant, so we need to change the frequency and as well as the field current that we have been provided at the rotor side. So this is the formula that we have been carried for its calculations. So we find out the frequency and the torque. Now the torque has been decreased from 208 up till 64.673 Newton. So this is the torque 7 that we have been achieved at this frequency and input field current, and this is the core losses. So this is the magnetic field density, almost is the same as at the above one. Now this is the curve, power and torque curve that we have been achieved from these results, that comparison of its torque and power. So the purple shows the power and the orange one and the blue one shows the torque. So this is the our constant torque region and this is our constant power regions. And the efficiency calculations of one field synchronous motor on the basis of these losses and that we have achieved is efficiency. So its efficiency at rated speed is almost 91.36%. So cost analysis. So we have been analyzed its cost on the basis of its materials that are used. So the main factor that affects cost in permanent magnet synchronous motor is magnet. So permanent magnet NDFEB cost is around to $50 per kg, while the copper winding used in wound field synchronous cost around is $10 per kg. There is a $40 difference on between the windings and the magnets that are used. So permanent magnet synchronous motor cost $250 excluding frame and fitting, while the wound field synchronous motor cost $140 excluding frame and shifting. Hence, wound field synchronous motor is less expensive as compared to permanent magnet synchronous motor. Conclusion. So we have been concluded that almost same efficiency as the our permanent magnet synchronous motor has been achieved. So operated of wound field synchronous motor at different speed, which is a basic requirement of electric vehicle motor, and high power and torque density has been achieved. So future recommendations, we do have certain recommendation that its power can be increased further up to 150 or 200 kilowatt as Tesla car new models have. And the second one is brushless wound field synchronous motor can be developed, and switched reluctance motor can be designed and compared with this model. So these are the references that we have been used while carried out our project. Thank you.